Hi, welcome back. In this lecture, I would like to talk about how to represent quantum negative integer numbers. So far, we have been using the quantum state to represent integer state, but only with values of 0 and positive values. In this lecture, we're going to look at an encoding technique to represent also negative integer number using the quantum states. The technique that we are going to use is a classical technique that is called the two's complementary binary representation. This technique is used by all modern CPUs and programming languages. And how does it work? Well, the trick is that we associate half of the values with the negative numbers and half of the state with the positive numbers for a given number of bits. So for a example, for a 3-bit register, we can encode 8 values. We use half of these 8 values for a negative number. So for instance, from -4 to -1, and half for null or positive values from 0 to +3. In the two's complementary binary representation, we are going to use the most significant bit for the sign. So the 0 corresponded to a plus sign, and then the +1 corresponded to the minus sign. So that also means that when we're going to look at our circular notation, half of the circle will correspond to positive integer, and then half of the circles will correspond to negative integer. Two's complements encoding works just as well for a register of qubits as it does for a register of bits, since it is really a classical technique. The important part is really to keep track of whether we are not encoding data in QPU register with the two's complements. Otherwise, we will interpret our binary values not correctly. There is a very simple circuit to start from integer, positive number, and then negate it, and is shown on these slides. So we have, in this case, a 4-qubit quantum register called A. What we do, we apply first a flip of all bits. So we apply a NOT gate to all the qubits, and then we apply a quantum circuit that we saw in the previous lecture, that is the increment operation. So very simple. So let's see an example of this negation operation, how it's going to work. The first step, as we know from a previous lecture, is to prepare our system in a superposition of a state. Also remember that we're going to use two's complements representation of integer number. This means that our state, in this case, half represent positive number, all right? And then when the most significant bit is equal to 1, this will represent the negative integer number. So we encode the state +1 and +5 using this quantum circuit. And then we apply the quantum circuit we saw in the previous slides. So what we want to achieve is -1 and -5. So the first operation is to apply this column of NOT operation. What we do, you see that we go directly on the second row, that is with the negative number. So this is negative and this is plus number. So still not correct. So what we do, we just apply an increment operation, and we go to this state here, from this one to this one. So remember, this is two complements representation. So this first is a plus, and this second is a minus, and this is the -1 values, and this is the -5 value. So remember that it's extremely important that we keep track that we are using the specific representation for representing negative quantum number. So in this case, this is not state 11, but instead is state -5, and this is not state 15, but is state -1. So this is the last slides of this lecture, and talk to you soon.